Hello everyone, and welcome to the MLT Edge AI Lab session, the Edge AI Lab with Microcontroller series. So under MLT, we have the MLT Edge AI Lab. So MLT Edge AI Lab was formed with the purpose of to provide an open environment to do experimentation. So it all started back in 2019 when we have a Hacker Farm. Hacker Farm is a small startup in Chiba where they asked us to visit their greenhouse. So they have a small greenhouse in Chiba where they work with agri-tech, and they try to implement suspended robot and try to see how machine learning can help into agricultural field. So we thought like we'll just we form a small team from MLT side, like some researchers and engineers, and we went there, visited their place, and try to talk with local farmers and local people there to understand what are the problems they are facing and how we can use machine learning to solve those problems. So that first session gave us an inspiration, like we need to do some hands-on workshops, or so that we can apply what we learn into real life applications. So we thought like, yeah, we should have this kind of like AI lab sessions, like hardware working sessions. So in 2020 we organized one weekend hackathon session with Robot Club. So wherein like we had a small space, and we provided them the hardware like Edge, Jetson Nano, Arduino, or Raspberry Pi. And then we ask members to do to form teams, like to start brainstorming ideas around this hardware and try to think about like how they can use this hardware to develop some good applications. And we had around, I think, 4 to 5 hours. And in those, like in that such a small time, we had around 4 teams, and 4 or 5 teams. We had 5 applications, like very simple applications, but they were demonstrated using machine learning and the ready available hardware. So we have, like, here you can see object detection, bounding box detection, and we use like device running on the Coral devices or Jetson devices. So that was our session. And after this was around, I think, February 2020, then after which we had the COVID. So for a long time we were not able to do any physical sessions, and we were continuously thinking how we should do this kind of like physical sessions. So again, last year we also participated in a online competition, like AI Edge contest held by Signet. And this was a competition wherein like you had to develop a object detection and tracking algorithm on autonomous vehicles. So we got a third prize in this competition, and that was like a small team from our this AI lab where we participated there, did work together even with work from home. And then after that, once after the competition, we thought like we would deploy this on a real instance. So we just took this model which we developed here and then deployed it on Jetson Nano. We did some 3D printing around printing the case of the Jetson Nano, and then deployed it on a bicycle. So this was all the like history where like the MLT AI Lab started growing like slowly, event by event. So if you are interested in this, knowing more or doing some collaboration around AI Lab, please join the AI Lab channel on MLT Slack. So with that, let me just introduce this series for people who are new. So the overall goal of this series is to build the applications by end of the series. So when we say build AI applications, right now, this series, we are going to focus on one of the microcontrollers, which is Arduino Nano BLE, Arduino Nano 33 BLE Sense. The reason why we chose this microcontroller was because it's really powerful microcontroller. It's readily available and a lot of sensors on board. So basically, we don't need to do a lot of circuitry, or we don't need to have a like detailed electronics background or skills. We can basically start from we can have a good start line to develop applications by themselves. So by end of this 4-week series, we are expecting like we'll have some teams who can build, document, and share the projects which they to the entire community here. So basically, we started with first session, which was last week. We just introduced, gave an overview of different AGI applications, what are the applications, use case, and the general purpose, block diagram, which is followed in AGI applications. Today, we have the second session, which will be mainly conducted by Naveen, and this will be like a motion-based application. So Naveen will be showing us a walkthrough to how to capture motion data using the Arduino Nano BLE 33 Sense board, how to use the IMU, and then develop an application on top of that. So with that, I think let us go to the introduction of a quick introduction of organizers. So Naveen, would you like to quickly introduce yourself?
Yes, thank you, Yuvraj. So hi, I am Naveen Kumar and I work at RIKEN. So RIKEN is one of the largest research organization here in Japan. And I mostly work with the microbial DNA genomics dataset to do some machine learning and mostly the data analysis. But I am also interested in these AGI projects, which I developed a few years ago. And I have developed many projects mostly at Hexter.io. So you can find my projects here at the hexter.io/Naveen BS Kumar. And you can see all different kind of sensor I have used with the different kind of use cases. So, and with all documentation, so that would be useful for everyone. And in my free time, I like watching movies and doing photography of nature and mostly playing with the microcontrollers. And you can find my new updates at my Twitter handle, Navin. Thank you.
Yeah, thank you. I mean, like when I told previous time, this wall is really nice. Like so many projects to try, and I myself want to try some of those projects. It's really nice. Okay, thank you, Naveen. And then let me quickly just introduce myself. I'm Yuvraj, Yuvraj Shinde, and I'm working as an engineering manager and a software engineer at an e-commerce company in Tokyo. And mainly, I love food. I really like to taste different cuisines, and definitely the second thing which I love is playing with robots, especially around kid robots, and also like trying to tinker around with kid robotics. So some of my past projects here, like when I started was like with Arduino, wherein like just try to make a simple model where not a model, like just sample data, how motors move, and then replay the same data again. So that is where I started learning about Arduino and machine learning and how I can improve models with that. Then I'm really like playing things around with Arduino and Raspberry Pi. So some of my projects were involved with Arduino are related to like these kind of like wherein in the second picture you can see a small humanoid robot, which is like an open source robot. I just printed it by myself. It's available online, so you can just print it and then developing an Arduino app around the top of that. And then the third one is like wherein like with Raspberry Pi, we're like thinking of building robot cars for kids where they can use stack of Raspberry Pi and Scratch so that kids can learn programming by themselves using Scratch. So that's my overall background. So let me just move to quickly next page. And here we are just showing the quick recap of from one of the slides of the previous session, which is like the generalized blocks of AGI pipeline. Wherein we start from data collection, storage, which partly occurs on edge, and the data storage partly occurs on cloud. And then you have the cloud pipeline. It could be a cloud or a PC, local PC, to train your model, test your model, and then transfer your model to again back to edge device, wherein you do on-device deployment and inferences on the edge. So with that, like a general idea, let me just hand over this to Naveen so that Naveen can now dive us into deeply into one of the applications like motion-based applications. Okay, so Naveen, can you please take it over?
Yeah, thank you, Raj. Yeah. So let me share my screen. So today we will mostly talk about the edge to cloud to again back to edge. So for this particular today, which we are going to make, actually I already made that project, but I will give you a walkthrough. So how you can collect the data collection, I mean how can you collect the data at the edge device, and how do you store the data or move to the cloud and do some kind of pre-processing which is needed for the feature extraction. And we do the model training, and we will do the model testing, and then if needed the quantization and post-processing, and then we will move the model to the device. So that is the online deployment, and we will show the demo of the online inferencing. So these all blocks of the AGI pipeline, we will, I will give a walkthrough. So first thing is this is the example of AGI application we can make using IMU. So IMU is an inertial measurement unit. So it is comprised of three kind of sensor mostly. So one is the accelerometer, and we can have a gyroscope, or we can have a magnetometer. So all the three sensors is already on board the Arduino Nano 33 BLE Sense. So we can make use of them. And these are actually 4 of the projects I have already created at hackster.io /Naveen BS Kumar. So you can access those with all documentation. And here you have all kind of, stuff to try out, like how you can collect the data using different sensor interfaces, and how you can display those data, and how can process that. So these are just an example for use cases. So one of the use cases I have done with the posture recognition. So posture recognition is like you are sitting in the good posture or bad posture. So the first device actually will let you know that kind of thing. So this is kind of wearable device. It's big actually, but it's just a proof of concept I have developed with this NRF53 board, development board. And another is the handwriting recognition. So in handwriting recognition, so one of the accelerometer and gyroscope, the sensor is actually tied to a pen, and then the training data is captured using this pen. So you just draw on some page and collect the data and then train. So when you, then the pen learns everything, and then it's just kind of amnest for writing all the digit from 0 to 9. And another project is like I have done with the activity of elephant. So with the public database, actually I took the database from the public repository because I don't have access to the elephant activity. So I used some different animal data set like sheep and goat, and trained the IMU and based on that. And then I showed like it can be, scaled for other kind of activity, other animal activities. And on the fourth one, that is the fall detection. So this is again the wearable device. So using this device, actually you can detect if somebody falls due to like aging or maybe some medical condition or something like that. So it will let you know like the activity is like real fall detect. Somebody falls down, then it will notifies you using the cloud. So these are just kind of the showcases of the some really good AGI application you can develop using the IMU only. Then before delving into today's project, so just have a primer for the accelerometer. So accelerometer is so first thing is the acceleration. What is acceleration? So acceleration is the rate of change of velocity of an object. So it's a very simple concept in physics, and we can measure the acceleration in either meter per second square or g forces. So g forces is like one gravitational unit. So on Earth, it is 9.8 meter per second square approximately, or it could be like 1/5 of that value if you are at Moon, or if you go to Jupiter, then it could be like 2.5 times of the Earth gravitational units. So it depends where you are, but we will be mostly dealing with the Earth units, of course. And accelerometer are electromechanical devices that measure linear acceleration. And this acceleration could be in the x-axis or y-axis and z-axis. So this is three-dimensional data it will generate. And accelerometer sense either static. So static forces are like gravity. So you are just sitting idle, but still you are exerting some kind of force. So that is the gravitational force. So accelerometer gives you that value. But if you are moving, then you have some kind of, for example, vibration or movement. So those kind of force are of dynamic nature. And in this figure, you can see like the ball is actually dropping from the top to bottom. So ball is actually accelerating. So the accelerometer actually measure that change of velocity of the ball. If you actually tie the accelerometer on the ball. And in the image below, this is actually the Arduino Nano BLE board. And this is, I think, we have taken from the Arduino website. So it actually shows the real orientation of the onboard accelerometer. So you can see like the g-axis is actually the perpendicular to the board, and x and y-axis is actually the horizontal to the board. So first we have to understand the vibration analysis. So what are the industrial use case for the vibration analysis using the Edge AI hardware? So vibration actually refers to the movement or mechanical shaking around the equilibrium position of a machine or part. So for example, in industry, I mean, there are a lot of mechanical parts, those moves, mostly using the motor or shaft, or there are many things actually. So they have actually inherent vibration. And vibration are usually periodic. There are some cases are there like vibrations are not periodic and they have a lot of noise, but usually they are periodic in nature. And the analysis of vibration actually allow us to evaluate the condition of equipment, for example, the motors, and avoid failures. So we can do some kind of predictive maintenance. So before something gets failed, we can actually predict beforehand, and actually we can notify the concerned department for the repairment. So this way actually we can actually overcome many issues in the industry and save a lot of costing for the maintenance. And vibration analysis also can be used in the structural health monitoring. So structural means like for the bridges or pipes or turbine blades. So they're actually, I mean, they have the structural health. So whether they are in good shape or is there any some kind of anomaly in their motion. So we can detect those kind of things using the vibration analysis. And there are two kinds of vibration for an object. So it could be free vibration. For example, if you just use the tuning fork, so those are free vibrations. You just hit the tuning fork and then it start vibrating and in periodic and harmonic motion. And there could be a forced vibration. So forced vibration means you are using some kind of machinery like the motor, like in the washing machine. So it vibrates using some kind of motor inside it. So those are the forced vibrations. So in the today's project, actually, we will using the vibration analysis to detect the state of the fan. So fan here we are using as a stand fan. So what we will do, so the aim of this project will be to detect the speed state of fan by vibration created by the motor. So we need some kind of sensor which we will mount or tie on the stand fan, and then we will measure we will collect the vibration data, and then we can classify whether the fan state is among the one of the four state. Like in the image, you can see that there are four state like off or low speed or medium speed, or fan is running at high speed. So we will understand the data collection process for this, and also we'll do the digital signal processing to extract the features. And we will see later like how a simple neural network model can easily distinguish these states. And also for this exercise, the coding is not required for simple working demo, but still source code will be available, and advanced user may customize the source code later, or maybe they can customize for their own use cases. So that would be the, I mean, this project will be the just the kind of demo, so they can get started with IMU. And we will be actually using Edge Impulse Studio. So Edge Impulse Studio is actually a online tool which have all set of tool chain. So using the GUI, so if we use their GUI, so we can actually do the all kind of signal processing and pre-processing, and we can actually clean up the data, and we can train the data, and we can make the bundle of the final firmware based on what kind of development you're using. So first thing is actually the mounting the device on the fan. So before moving into the real coding and the data collection, first we have to deal with the hardware setting. So you can see in the picture, so there is a stand fan, and I have actually mounted the device on the rear of the fan in horizontal position, just above the where the motor is actually inside the casing. So we will use a rubber band to secure. So we should not secure very tightly and not so loose, just the optimal. The Arduino Nano 33 BLE Sense on the rear part of the stand fan near the motor, and we can keep it in any orientation just for the training data collection, but horizontally is more convenient. So you can actually reproduce every time. If you remove the hardware, so you know where you have put it. But it's okay, I mean, if you want to train the data based on different orientation of the hardware, so this way actually your model will be more robust, and you can put later in any orientation. But for this particular exercise, we will just train using only one position. And keep the USB cable plugged in to avoid disorientation. So once you mounted the board, so just keep the USB cable plugged in into the Arduino Nano BLE Sense board. So by mistake, you don't move the board if you plug unplug many times. And don't pet your cat while handling or about to handle your microcontroller board, because when you do that, so it generates some kind of electrostatic charge in your hand, and then the microcontrollers are usually not very, I mean, they are very vulnerable to the electrostatic charge. And not only microcontroller, but there are many IC chips on the Arduino Nano BLE Sense board. So you don't want to blow up your board using the electrostatic charge. So first thing is the data for the data collection. So you have to actually create a free account at edgeimpulse.com and create a new project. So this step is very easy. You can do anytime. And you have to install the Edge Impulse CLI. So this is the URL for the Edge Impulse CLI installer, but you can search these things on their website. So they have a really nice documentation. And then we will actually download the Edge Impulse firmware for the Arduino Nano BLE. So actually, at the Edge Impulse Studio, they have created different firmware for the Edge devices they support actually. So fortunately, they are supporting Arduino Nano BLE Sense. So they already built the firmware for the data collection. So this firmware actually have all the library. They include everything, and you can actually download the firmware in binary format, and then you will have a bundle of a zip file, and you unzip this bundle when you download at your local machine, and they will give you 3 commands within that bundle. So first you connect your Arduino Nano 33 BLE Sense to your computer using the USB cable, and then open the Flash script for your OS. So when you unzip your bundle, the downloaded bundle, so you can find 3 script based on your OS. You can choose one of either Mac, Windows, or Linux, and just run that. and it will automatically burn. It will automatically identify the board attached with the USB and just burn the firmware. So you don't have to do anything, just run this command. And once you are done, just reset the board. So this way the firmware start running or executing. And in the point 2, actually we installed the Edge Impulse CLI on our local computer. So they will provide you an Edge Impulse daemon. That's the command line tool. So you just write this command at the command line, edge-impulse-daemon, and it will start actually connecting to the Arduino board. And the project actually you have created at the Edge Impulse. So this daemon actually asks you a few questions interactively, like what project you have created at Edge Impulse. So it will show you the menu of that project. Then you can, if you have only one project, then easy to choose. But if you have many projects created, then you can choose one of them where you want to upload the data from the microcontroller. And then once you are done with the data collection, go to the data acquisition page as the Edge Impulse Studio and start recording new data. So I will show you the walkthrough of the demo using the video, so you will have better understanding of that. And you can find all this information in our GitHub repo. So later Yuvraj will let you know how you can access those things. So you don't have to remember everything right now. So this is the first process of the, so before actually moving to the Edge Impulse, we will talk about the process they will be doing, but the process they will do at the cloud is kind of black box, but actually we want to understand how they are doing. So I will show you like what kind of tools they will use. So actually Edge Impulse use mostly the open source toolset and tool sets and the SDK, and they are just wrapper on the TensorFlow Lite for microcontroller SDK. So they are actually giving just a nice view over all the open source SDK. So we will be not bound to the Edge Impulse, but it's good for the showcase and prototyping and quick demo. So I have chosen that platform. So first thing is the digital signal processing. So for the digital signal processing, so we will have the accelerometer data. So for this example or project, we will only use the accelerometer. We will not use the gyroscope or magnetometer from the IMU. So only one sensor. And so the raw data of the accelerometer will be in the time domain. So time domain means that is the time series data. And then we will actually scale the data. It's up to us. Do you want to scale the data? So it depends on the use case. So suppose if your data is very, you cannot, it's very small scale data, for example. So you cannot actually visually look at data. So, you like to scale just for visualization maybe sometimes, and sometimes you just want to zoom into your data for better model training. So it just depends on your use case. So you may or may not do the scaling. So for this project, we are doing the scaling of 1. So that is doing nothing actually. But I just keep for your information, so you can do the scaling like 2 times, 3 times, or multiply with any floating point number. And we do the normalization after scaling. So normalization is mostly the doing some kind of adjusting the accelerometer value within some ranges, like subtracting the mean, or you can divide with some value to keep the value within some ranges. And for this project, actually, we are using the high pass filter, but actually you can also do the low pass filter. So it again on your use case, like what kind of application you are going to make. Suppose you are going to make a very fast moving object detection, or maybe something like there are a lot of movement, right? So in that case, you want to remove those noises which are like using the low pass filter, right? So you don't want to come in the very high frequency noise in your data. But for the vibration, actually, data is actually most of the time very consistent. So even if you don't use the filtering, that will work. But for the sake of removing the very low noise in the data, so I have used the high pass filter. And after that, actually, we will use the fast Fourier transform to convert the time domain data into the frequency domain. So why we are doing this? So extracting the feature from the raw data is not easy. So there are two ways to do the feature extraction from the accelerometer data based on your use case, of course. One is you can actually use just statistics, like you just calculate the average or just calculate the moving average for example, for each 10 values, or maybe windowing 10 values and just calculate the moving average, or you can use the skewness of your data, or any kind of normal like descriptive statistics things you can calculate using the raw data in the time series domain. But those data actually will not able to differentiate between very low difference between the vibration analysis, because I mean those values will be very close, so it will be very difficult to distinguish. So we will also use the frequency domain features, which are more robust and they are actually stand out visually. Also, you can actually distinguish between the data. So later I will show you how. And once we have done the fast Fourier transform FFT and convert the data into the frequency domain, so we would be easily calculate some different features from that data. So in next slide, I will show you what are those. So in this figure, so first we'll talk about the 3-axis accelerometer raw data. So you can see this raw data as a numbers. So it is just you can see as a array of 3-dimensional array, right? So each row has 3 values. And the data is actually sampled at the rate of the 100 sample per second. So that is 100 Hertz. And this is the visualization of the data in time domain. So I just visualize the raw data, and you can easily see. So the G-axis data actually stays mostly near the top value, around 9.8 meter per second square actually. And all X-axis and Y-axis data is near 0 or 1, because they are actually vibration is actually very small in this case. And when you convert the data into the frequency domain in the image below, so you can actually see the periodic nature of the raw data. So the raw data from the time series is now become the frequency domain data. And now we can easily calculate the other feature. So mostly we will be dealing with the 4 feature here, but there are many other features. So if you have better understanding of spectral analysis, so they will provide many other features also. But these 4 features are suffice for this kind of practice. So we will use the root mean square RMS. So RMS is actually directly calculated from the time domain. And then peak height, peak frequency, and spectral power. These 3 features are calculated from the frequency domain. And you can see in the figure on the right side. So the first figure is actually the normalized output of the, so normalization is actually done by the mean subtraction and applying the high pass filter to the raw data. And the image below is the power spectrum using the FFT. So power spectrum is just the, you can think the power spectrum in terms of amplitude. So amplitude of the waveform. So amplitude is the maximum displacement of the wave in any direction from the 0. And power is actually the square of the amplitude, just for your understanding. So those features are actually, I mean, very strong feature. So we can actually distinguish between 2 different states easily using these features. So I will show you the one of the video I have captured for whole process using the Edge Impulse Studio. So we will show you how you can do these all blocks of Edge AI pipeline from the digital processing to creating the model during this video. So actually, I will not show the video in continuity. I will stop video, and wherever I have to talk about something, then so just the combination of many slides. So first thing, actually, you have to create a account at EdgeImpulse, and then you will create a project. So here, actually, I created a project, fan status detection using vibration. And this is the dashboard of the EdgeImpulse Studio. And then first we have to go to the data acquisition tab here, the link. And in data acquisition, you can see I already have captured many data already, but you will see how you can capture one in this video. So for this data collection thing, it is assumed you already connected the Arduino Nano BLE through your PC, and you already started running and your Nano BLE board already have the firmware downloaded from the EdgeImpulse. And then you have to start this command line. So first time, actually, you have to run this command line. Then it will ask you your username and password of the EdgeImpulse. So this command line will connect to the cloud, right? And it will sample the data locally and transparently send to the cloud. So seamlessly. So you don't have to worry about uploading the data. So this data, this daemon will connect to your board, your edge device, and also the cloud, and communicate in between. So it's kind of broker agent, something like that. So once you run so I already run this command line before, so it did not ask anything like my username and credential. So from the next time, it store everything on your computer, and it will not ask if you have already run this command. So it will actually connect the board automatically. So it finds the board on this the device. So this is the device ID on your computer. So it could be different. So I am using Mac OS, but on Windows it's usually COM1 to something like that. And in on Linux machine it is something different, like SS, something like that. So it could be different. And so it is connecting with the EdgeImpulse Studio, and it will ask the name of the device. So it will actually generate automatically some hex ID for the device. So you just go with the default. And once it is connected to the device, we will back to the data acquisition page. And on the right side of the data acquisition page, you see the record new data. And you can see the device is already connected. So you will see that device ID here on the top field. And we can choose actually built-in accelerometer, but it also actually can sample the microphone. So that firmware we have bound into the Nano BLE has the both for the provision for the both microphone and the accelerometer. So we already chosen the built-in accelerometer, and actually we can choose the frequency of the data. So for this example, we are having the sample length of the around 10 second of the and 100 hertz of the sampling rate. And once you click start sampling, it will just wait for 10 seconds for the sampling the data. And once the data will be sampled, it will be automatically uploaded, and you can see in this table. So that will appear as a first row. So yeah, it is done, and then you can see this is here, and the data visualization is there. You can see here is the data just been uploaded. And we move to the this create impulse. So before actually moving to the DSP process, so we have the all data. So I already uploaded the data for the 4 states, like high speed, low speed, idle, and the medium speed. So we have the balanced data set. And then we are going to pre-process the data. So for the data, the nature of the data is the time series. So I have added one of the block in here. So this block is actually by default appear when you open this page. And here actually I choose the window size of the data, 100 millisecond. So that is 1 second. And window increase is 80 millisecond. So actually it will scan your data. It will take 1000 millisecond of data and scan the data with the 10 milliseconds of sliding window. And each sliding window is kind of, it will try to extract the feature from that. And for the processing block, actually they provide many processing block. So I have chosen the spectral analysis, which I have talked before. And then for the classification, we will use the classification using the keras, that is the TF light keras. And then you have to save this. Once it is saved, we move to the generate data page that will be automatically rerouted. And here in the generate data page, actually first we have to define all the things. So for the scaling, I have defined, just keep things default. So 1. So 1 means I am not doing anything, no scale. And filtering, actually we can choose the low pass, high pass, depends on your data set. And for spectral power, you can choose the FFT length. So I will go with the default setting, which is good enough for this particular exercise. So FFT length is 128, and there are a number of peaks and the peak threshold. So peaks are actually the power peak of the FFT edges. So just in your graph, you have the peaks. So it will record those peaks as a feature. And the left side picture is the same as we discussed before. Sorry, right side of the picture. And then for this exercise, actually, you can either choose the high pass filter, or you can also choose the none, because there are not much noise in the high and frequency, low frequency domain. And then once we are done with all the parameter configuration, so we go to the generate feature tab. In the same page, there is 2 tabs, parameter and the generate feature. And in generate feature tab, just click on the generate feature, and it will actually generate all the feature. So I will actually fast forward this part because it will take a bit time. So it is generating the feature. So once the feature is generated, you can easily see the feature in the left side of the panel. There is a feature explorer. So you can see the features in 3-dimensional view. So you can see all the features like high, idle, not feature, all the states, high, idle, low, and medium. You can visually actually, see they are actually separated based on the feature we have extracted. So those features are actually RMS or the spectral features and the peak and height of the spectrum. So actually the model can easily distinguish between these features. And once we are done with the DSP things, we will go to the NN classifier link here, and it will show you this page. And in this page, actually, it will give you a view. You can select the all kind of layer, which is available in Keras and TensorFlow 2 Keras. But I have only chosen the dense layer with only 8 neurons. So this is one of the simplest model we can define for this kind of data and see how does it perform. And also there's one of this button here, a menu. So you can switch this view into the Keras view, and you can actually edit your code. So all the code will be shown if you change the view. And click on the training button, and it will start training. So I will again fast forward this part, so it will take some time. So you can see just the Keras training, and you might be familiar with this console log, which is displaying on the right panel. So showing all the validation loss and the accuracy. So once the training is done, so actually it will create all the so you can see here, it is showing the confusion matrix. So there are two kinds of model actually it generates. One is the quantized and one is the unoptimized float values. So actually you see in the quantized value, accuracy is 90%, but there are some kind of, confusion in the low value and the medium state, because they are very not much, differentiated using the existing data or existing feature. So if you move to the unoptimized version, so we see like everything is very clean. So we are going to use actually the unoptimized version. So that's the point actually I want to discuss here. Like quantization is not always a good thing. Sometimes it will not give you a correct accuracy. And if your microcontroller allows the size of the floating point model, so you can actually use that. So that is okay. So you don't have to always use the optimized quantized model. So in this case, we are going to use the unoptimized floating point 32-bit model, because this has the 99.5% accuracy and really good and very low loss. And once we are done with the training, we can go to the we can go to the testing. So there is one model testing page. In model testing page, actually I have collected few data which were apart from the testing training data. So this data actually we will see how our model is performing. And we will click on the classify button at the top, and it will actually run on the new test data. And once it is done, so we can see the output here. So it performed 97.46. So it's a really good model. So only using 8 neurons, 1 dense layer, but using the correct DSP and data processing, data extraction, feature extraction. So those are actually important part of this project. So if you've done the data pre-processing and feature extraction in good way, so even a simple model can differentiate between the features easily. And we can also actually do the live classification. So live classification means we can take the data directly from the microcontroller and using the edge impulse live data. So this is the edge impulse live data classification page, where we can actually sample the data from the live microcontroller. The microcontroller is already mounted on the fan, and we can use one of the fan state and see how does that work. So I am sampling only 2 seconds of data here actually, and same microcontroller with the ID, and actually in the command line the same edge impulse daemon is running. So the microcontroller is connected to the cloud actually. And once we start sampling, so it will gather 2 seconds of data and start classifying after that. And we can see it will actually classify the data on the window size, which we defined like 80 milliseconds. So we see all, so actually I gathered the data of the high speed of the fan. So it is actually 100% correct during the classification. So you see in the high, all are 1%, sorry, 100% accuracy. So 1 is the highest probability of the classification. And after the testing, we can go into the deployment page. So there is one deployment page here, and you click on the deployment page, you can choose what kind of deployment you want. So since we are using the Arduino Nano BLE, so we will choose the Arduino SDK. So everything, all the DSP code, all the pre-processing code, scaling, normalization will be captured in this bundle, and all the inferencing code will be there. So we will walk through that code later, and we can actually download that to our local computer, and later we will burn that firmware into the Nano BLE. So I have chosen the unoptimized version because that worked really well, and then it is downloaded to our local PC. So that part actually concludes the model training and data collection thing. So maybe if you have a question, then I can take that now.
Yeah, I think we can continue. Maybe we can take the questions together in the end. We are a little bit running behind the time. So,
yeah. Okay. So this is the online on-device inferencing demo actually. So you can see the real image, real video of the fan. The microcontroller is actually mounted on the fan. In the same position, we collected the data. We are doing the inferencing. So the bundle we have downloaded just now in the previous video. So actually, I compiled that bundle using the Arduino IDE. So actually, to compile the bundle, we just have to include the bundle. So bundle actually comes as a zip file. And if you go into the Arduino IDE, so there is an option. So include library as a zip file. So you use that include zip file as a library. So all the code will be part of the Arduino SDK library. And then we can use one of the sketch to run the inferencing example. So here actually I'm going to show you the example. So in this video actually, so there are actually 4 modes. First is off. Off is idle, right? So you can see on the screen. So I am showing the output in the using the serial monitor, and the microcontroller is actually connected over the USB connection, USB serial connection to the laptop, and it's showing in the laptop monitor. You can see all the 4 probability of the classes, and there are 4 colors actually, same as this image. Like low is blue, medium is green, and high is actually red. So I will start changing the state of the fan. So you will hear the sound of changing, switching the button, and you easily recognize which mode it is doing. And you can see at the inferencing console output. So you will know how much like probability or how accuracy is that for particular classification. So it takes 2 seconds to sample the data and do the inferencing. It's running the low mode and collect the data. Medium, the LED changes. High mode becomes red. Again, go back to the medium. Going back to the low mode. It takes time because of the sampling. Then off, then all switch off. So that's the demo of the inferencing. And I will give the quick walkthrough of the code which we are running on there. So I will open so this is actually code for the inferencing. So the first line of the code includes the library we have downloaded, and this library actually we included using the Arduino. So this is the part of the SDK now, and all the inferencing, DSP, and data processing codes are in this library. And the second line is the Arduino LSM DS1 library, which is the library for the IMU we are using. And we will only use the IMU accelerometer. And these are just some definition for the conversion. And in Arduino, we have only mostly two functions in the main sketch, that is setup. So in setup, we have set all the RGB LED things as our output. So for the displaying the output. And then here, just this IMU is an object. So once we included this Arduino LSTM, so this IMU is available as object. And just begin this. So begin is just initialize the IMU. And in the loop, so loop is running. It is actually, it's kind of while loop. And it's just in this loop, actually we are sampling the data from the accelerometer, which is connected to our laptop. And it's storing the accelerometer data in the buffer as a one-dimensional array with some delay. And once the sampling is done, so we use the edge impulse SDK function. So that is run classifier. And there is one signal. So this signal is actually do all the heavy lifting of the DSP coding. So you just pass the buffer to signal from buffer function from the SDK is impulse SDK, and it will calculate all kind of, DSP, preprocessing, other things, and give the feature back to your classifier. And once we run the classifier with the signal, it will automatically extract the feature and pass to the model. And then in this loop, actually, we are calculating all the classification results, just displaying actually. And based on the maximum probability, we are actually turning on and off the RGB LED light. So that is very simple code. So you can actually easily use in your own code, or maybe make some different display thing, or use BLE to send notification for something. So this is just a showcase of this demonstration. So I think I am done with the all my stuff. So Yuvraj, maybe you can take the control.
Yeah. Thank you, Naveen. I think that was a really great